Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks for inviting me and giving me a chance to talk here. I'm going to be talking on Gibbs measures on trees and random graphs, and work I've been doing with Elkin and Mosul over the last year. And so the sort of common theme going through all the problems we've been working on has been sort of to look at the properties of Gibbs measures on trees and say, what does this tell us about other things, properties of Gibbs measures on other graphs, and in particular random graphs, because locally they look like trees in most of the play. And so you'd expect some of the behaviors of Gibbs measures on trees to carry over. And so in particular, we want to know what does the spatial mixing properties on of Gibbs measures on trees tell us about spatial mixing, about properties like of spatial mixing properties on other graphs, and also temporal mixing properties, by which I mean the mixing time of the Glauber dynamics. And so the main thing I'll be talking about will be the looking at what we can say about mixing times on Erdos Renyi random graphs, particularly for the easing model, but also for coloring models and other models. So just to briefly go over some background, a Gibbs measure is, as I'm sure all of you know, is sort of a probability distribution on configurations. So we have a graph with vertices V and some finite set of states A, and a configuration is an element of A to the V. And a Gibbs measure is a probability distribution on these which satisfies a Markov random field property, and be given by sort of potentials, a Hamiltonian sort of given by potentials on the edges, and these weight the distributions. But to talk about sort of the same models on different graphs, we'll expect sort of some kind of homogeneity of the potentials. So they'll be of the form of the Hamiltonian will be a sum over the vertices of some fixed function of the spin, and plus a sum over the edges of some fixed function of the spins on the edges. And some examples of these that we'll be interested in will be random colorings of the graph, so where we have a set of colors and we color each vertex in such a way that adjacent vertices have to have different colors, and the random coloring model will just be the uniform distribution on such colorings. And the easing model, where each vertex gets a plus or a minus, and the Hamiltonian will be the sum of the product of the spins across edges times some parameter beta, the inverse temperature. And so we'll be interested in how, as beta changes, the property of the Gibbs measure changes. And okay, so just to go over some definitions of spatial mixing that we'll talk about. The first, so sort of the natural question to ask with Gibbs measures is, are sets of vertices, which are a long way away from each other, related, or do the sort of correlations between them decay with distance, or are they still sets very large distances apart, still dependent? So there are several notions measuring this. Uniqueness says if we take a vertex V, can we, by conditioning vertices a very long way away, affect the distribution at V? Okay, you're right, that's true. So I didn't want to make the slides more complicated, and so for strong spatial mixing, it's a similar definition, except now when when we choose two sets and condition them in two different ways to see if we affect the distribution at V, you can also include vertices close by to V, but when you sort of condition them in two different ways, the vertices close to V have to be conditioned to the same thing. So this is a stronger mixing property, but in general, but in a lot of models, the sort of thresholds are the same, but not always. And reconstruction, we mean if we fix a vertex, the spin at a vertex, and look at the spins at vertices a long way away, does that give us any information at the vertex V asymptotically? And the hierarchy of these are that strong spatial mixing implies uniqueness, implies non-reconstruction. Okay, and by temporal mixing, I mean mixing of the Glauber dynamics. So this is or alternatively called the Gibbs sampling or the heat bath, and so this is a Markov chain which is commonly used to sample from Gibbs distributions, and it just works by vertices are chosen for updating, and then the spin at that vertex is erased. Then you calculate the conditional distribution at the vertex given the rest of the graph, and then update the spin according to that conditional distribution. And what we'd be interested in here is, as we let the number of vertices grow in graphs, is the mixing time polynomial in N, or does it grow super polynomially? Or essentially equivalently, is the relaxation time 1 over the spectral gap polynomial in N? Or we're also interested in cases where the spectral gap will be bounded as N grows. And so why look at these things on trees? Well, the main reason is that you can actually calculate a lot of these, the thresholds for these behaviors on trees exactly. And so there's been quite a bit of work on this sort of thing. And so the sort of trees, I mean, like the regular trees or trees that arise from Galton-Watson branching processes. And so for the easing model, all these thresholds are known. For uniqueness and strong spatial mixing, if d times hyperbolic tan of beta is less than or equal to 1, then you have uniqueness and strong spatial mixing. And you have reconstruction if d times hyperbolic tan squared of beta is greater than 1. You have polynomial mixing for all beta, and bounded relaxation time if you have non-reconstruction. Okay, and so random graphs are sort of a next step to looking at these sort of problems, and or a next model to look at, because they're locally tree-like, but also have loops, and the behavior. The behaviors are not always the same. So we want to know about look at the supercritical case where the probability goes like d over n for d greater than 1, where there's a giant component. When there's not a giant component, it'll just be sort of like the tree cases again. Okay. And so locally, and so the structure of random graphs is very well known, and locally they behave very closely to, and you can couple them to, Galton-Watson branching processes with Poisson offspring distribution. Okay, and so just to summarize, the overall theme is to take models on different trees, look at their spatial mixing properties and thresholds, and sort of try and relate these to behavior on more general graphs, to say things about the spatial mixing properties, but also the temporal mixing properties on more general graphs. Particularly random graphs, but you'd also like to be able to say things on more general graphs, or at least in terms of bounds. So some things are known in this sort of regard. So Draw-Whites showed that in two-spin systems, strong spatial mixing on the d-regular tree implies strong spatial mixing on all graphs of maximum degree d. So spatial mixing is sort of, so the tree here is sort of the extreme case for spatial mixing, has the strongest correlations. Other sort of results relating these thresholds have been proving that you have slow mixing, exponentially slow mixing, when the parameters are above uniqueness thresholds. And so, for instance, Montanari showed that you have slow mixing on the, or results of his show that you have slow mixing on the random d-regular graphs, sort of, or asymptotically every random d-regular graph when you're above the uniqueness threshold on the easing model. And this is by sort of standard conductance methods, showing that you have where there's a bottleneck going between sort of zero, sort of small magnetizations, and so it's the Glauber dynamics takes an exponentially long time to get. Well, so the mixing time is exponentially large in the degree. Okay, so Draw-White's result using his tree of self-avoiding walks applies to two-spin systems. And the first problem Elkanan gave me was to say, can we apply this to systems with more than two spins, so colouring models and that sort of thing. And it sort of became clear that just trying to extend his this construction to something like the colouring model didn't work, and so we wanted to say, and so the idea of this would be to try and prove that in any Gibbs measure, strong spatial mixing on the graph implies strong spatial mixing on a deregular tree implies strong spatial mixing on any graph of maximum degree D. And so if you look at the boundary of a ball of radius r in the deregular tree, it has more vertices than for any other graph, so there are more vertices to condition on, and you might expect this gives you the strongest correlations. But this intuition turns out to be wrong in general graphs and systems where you have more, you have multiple spins, or at least in one particular such system. So we looked at antiferromagnetic Potts models and found that the correlations in some graphs seem to decay more slowly on particular graphs than on the corresponding trees. But we couldn't quite come up with an example where to sort of to say that we have strong that we have sort of some kind of spatial mixing on a on the tree but not on the graph. So the graphs I'll show in the next slide. And so we extended, so we took an antiferromagnetic Potts model with K states and then added an extra state with different interactions. And then on the K+1 regular tree, this model has uniqueness for sort of large enough K, and but on this K+1 regular graph, which we build by connecting up K cliques, and you imagine this is actually an infinite graph, but where each of these are K cliques. And if you analyze sort of the recursions of the our Gibbs measure on this infinite graph, then you don't have uniqueness. So this is an example where uniqueness on the on a K+1 regular tree does not imply uniqueness on all K+1 regular graphs.
What is this lambda?
So lambda was just a sort of parameter in the model. So so it has parameters lambda and beta sort of represents the interactions of the antiferromagnetic Potts model. So then we don't know. So we don't. So it may be the case that in monotone systems, say, or like ferromagnetic ones, that this sort of the tree is still the extreme sort of case, and we sort of crucially use the anti-ferromagneticness of the model to come up with this example. So like when you have sort of colourings with K colours, then sort of in a K clique, you're going to get all of the colours sort of with, and so that's why it's important. And so the crucial difference the crucial difference between the graph and the tree is that in the graph, by sort of having dependencies between the vertices next to the root, because we've got edges between them, you can much better control the spin at the root. Okay, so now changing tacks, I'll talk about the Glauber dynamics on Erdos Renyi random graphs. And so the question here is, when d, the parameter in the Erdos Renyi random graph, is greater than 1, for which beta is the Glauber dynamics polynomial in n? And there are some technical hurdles in proving polynomial mixing times on these graphs, and the biggest one is the fact that the degree grows with n. And
if you didn't have just that one hurdle, there wouldn't be any obstacle.
Oh, that's right. Yeah. No, that's exactly true. Just the, yeah. And so,
as long as you want to work with existential data, as long as you don't want to go all the way to
yeah. So yeah, this is the key hurdle, and so the problem was, do we have polynomial mixing for any beta? So Montanari results show that when d times hyperbolic tan of beta is greater than 1, then we have slow mixing. And this factor corresponds to the uniqueness threshold for the easing model on the Galton-Watson tree with Poisson D offspring distribution. And plays an important part in the results. So the result is that when d hyperbolic tan of beta is less than 1 on it.
How by one thing about d versus d minus 1?
So So d will, yeah, so, yeah, so, okay, so this is so if it were a d plus 1 regular graph, then, or if it were a d regular graph, then you'd have a d minus 1 here. But sort of as you expand the tree around a vertex, okay. And so we've shown that when this is less than 1 on e squared, you get polynomial mixing of the Glauber dynamics for almost every graph. And we conjecture that, in fact, d hyperbolic tan of beta less than or equal to 1 is the correct rate. And I'll talk a little bit more later on about why we believe the conjecture is true and why our proof doesn't get up to that. So sketching the proof, the first thing we analyze is the Glauber dynamics on a local neighborhood of the graph. So taking a vertex and looking at a ball of it around it. And this will be a tree with some bounded number of edges. And removing the extra edges affects the relaxation time by at most adding or removing an edge affects the relaxation time by at most a factor of e to the 4 beta. So to analyze the mixing time, we can disconnect the root of a tree from its subtrees, and this affects the relaxation time by a factor of e to the 4 beta times the degree of the root. And now in this new graph, the relaxation time is just the maximum of the relaxation times of the subtrees. And so by induction, we get a bound on the relaxation time on the tree of e to the 4 beta m, where m is the maximum over all paths from the of the sum of the degrees from the root to the leaves, maximized over all paths from the root to the leaves. And this means that when we look at, for any vertex, if we look at a ball of radius just a bit smaller than a half log base d of n, then we get polynomial relaxation times.
So the tau relax here is for the continuous time dynamic?
Yes, yeah. Which is related to the, yeah. And so we complete the result with a coupling argument. So we let x minus and x plus be copies of the chain started in the all minus and all plus configurations, and you take the standard monotone coupling of the Ising model. And you want to analyze the mixing time. So work out when there are no more disagreements. And we do this for each vertex by creating 4 new Markov chains. And this is a sort of fairly standard argument. So we create chains Q minus, Z minus, Z plus, and Q plus on the subgraph of a ball around the vertex. In Q minus and Q plus, we fix the boundaries to be all minus. In Z plus and Q plus, we fix the boundaries to be all plus. In Q minus and Q plus, we start from the all minus and all plus configurations. And Z minus and Z plus, you start from the stationary distributions. And so we can couple them so that Q minus is less than or equal to Z minus is less than or equal to Z plus is less than or equal to Q plus, and couple it with the Markov chain, the Glauber dynamics on the whole graph, so that Q minus is less than or equal to X minus is less than or equal to X plus is less than or equal to Q plus. And so a disagreement at Q, a disagreement at X will imply a disagreement at Q, and then we can just bound the probability of this. And so if we run the Markov chains until time t, where t is sort of a bit more than the relaxation time that we calculated in the last slide, then with probability little o of 1 on n, q minus and z minus will have coupled, and q plus and z plus will have coupled, and so the so we just need to bound the probability that there's a disagreement between z minus and z plus, and this you can do because you know that they're in the stationary distribution, and so you can use the spatial mixing properties on the trees, and you get, and so the probability that they're different is something like this, and this is where the decay of correlation comes in, and this is also where our proof, the reason why we don't think our proof is sharp. When d hyperbolic tan of beta is less than 1 on e squared, this is enough to ensure that this term is the low of 1 on n, and so this ensures that the probability that x plus and x minus have a disagreement at v is the low of 1, and so this is a bound on the mixing time. And so this implies polynomial mixing and completes the proof.
So R is chosen such that almost surely this ball is a tree?
R is chosen so that almost surely this ball has, that if you take any vertex in the graph, there's some constant kappa, say, and there are at most kappa it's a tree plus at most kappa edges.
So why is it kappa?
This, yeah, so this is sort of, this means that the ball is of size about, has volume about root n, and so if things will, when it gets bigger than that, things will start connecting up again. So what the proof says is that, so this leaves open what happens between 1 on e squared, well, when d hyperbolic tan of beta is between 1 on e squared and 1, and but it says that for any vertex in the graph, the probability that after some time you have a disagreement is the low of n to the minus gamma for some gamma between 0 and 1. So after a while, there are very few disagreements between x minus and x plus, and we believe that sort of this implies that there are no disagreements, but we haven't been able to modify the proof to complete this. And so if you...
It seems to me that you don't need all the vertices to be coupled, right? Because if you have a tree-like structure, you need only the vertices, say, on the leaves of the local tree. I know that that doesn't beat this problem, but maybe you can build a strategy around that.
We've been trying to do that, and yeah, haven't been successful with that yet. But yeah, that sort of a, hopefully that sort of approach will work, and it again suggests that the conjecture is true. Okay, so
Agreements, they're rare, and also they're not very, they don't percolate, so they're kind of small clusters.
yeah, and
their probabilities, yeah, okay.
yeah, and like the probabilities are also small everywhere, so they're not necessarily happening at the very high degree vertices either. And so, like, what I think happens is that the mixing time sort of relates to when sort of you get rid of all the disagreements at the very high degree vertices. Okay, so this the proof heavily relied upon the fact that the easing model is a monotone system, and so it doesn't apply to the antiferromagnetic easing model and doesn't apply to colourings or the hardcore model or most other models. So the question is, can we get polynomial mixing for these ones as well? So this was Dyer, Fries, Flaxman, and Vigoda, I think. And so they had a paper saying you have that if you take a slightly modified chain and let the number of colors grow like something like log n on log n, I think, then you have n log n mixing of this chain. But they had to allow the number of colors to grow with n, and ask the question, can you prove polynomial mixing with a constant number of colors? And so here the interactions are hard. So this involves a whole lot of extra issues. So for instance, we can't just remove an edge and affect the relaxation time by a constant factor.
When you say constant number of colors, do you mean like bigger than B?
Yeah. And bigger than that as well. So
Not growing with A.
yeah. And so right. And so we've shown this by doing a block dynamics argument and partitioning the random graph into appropriate blocks. So in particular, we want each of the blocks to either be a tree or a tree plus some small number of extra edges. And we want all any cycles within a block to be a long way away from the boundary, so that close to the boundary of the block it looks like a tree. And we can ask for some other properties, like that blocks only meet across one edge, that their blocks aren't too big. So this will be sort of for some parameters L, kappa, alpha, and epsilon. And the final and most important property is that if we take for the vertices on the boundaries of the blocks, so we have this condition, so we sum over all the vertices in the graph of alpha to the power of the distance from the vertex u, sort of being the boundary vertex, to v, and we want this to be bounded by some number epsilon. And this will ensure that there aren't high degree vertices too close to any of the boundaries. And with these properties, we can do we can look at the block dynamics, which is like the Glauber dynamics, where rather than updating one vertex at a time, we update a block at a time by taking you erase the spins in the block and update it based on the conditional distribution of the rest of the graph. And a standard path coupling argument is enough to show that the relaxation time of the block dynamics is polynomial in n, provided we have enough colors. And then the relaxation time on the whole of each of the Glauber dynamics on each of the blocks is also polynomial in n, and bounded by some polynomial in n. And the relaxation time of the Glauber dynamics on the whole random graph is therefore, by a standard result, bounded by the product of the relaxation time of the block dynamics times the relaxation time of the maximum of the relaxation times of the Glauber dynamics on the blocks. And so this shows that if we have sufficiently many but bounded number of colors, then we have polynomial mixing. And this argument also extends to general sort of models with soft constraints at high enough temperatures, so the antiferromagnetic easing model, or the hardcore model with low fugacity, but doesn't give very good estimates of, and doesn't get anywhere near the correct threshold. And for the coloring model, as well as for the antiferromagnetic easing model, the correct threshold for polynomial mixing is conjectured to be the Reconstruction threshold rather than the Uniqueness threshold. And so we're not even close to getting to the Uniqueness threshold. And how to prove sort of any sort of mixing results below the, or sort of above the Uniqueness threshold is, I think, a long way off, at least for me. Okay, and so some open problems I'm thinking about in this general vein. So can we extend the example where we had uniqueness on a d-regular graph, but not uniqueness on the d-regular tree to strong spatial mixing? The example I had doesn't seem to be an example for this. I mean, one difficulty in showing such a result is that it's generally just hard to establish thresholds for strong spatial mixing, particularly in multi-spin systems.
So the example you had was for the uniqueness, but not for the strong.
That's right, yeah. And so I guess this should be d+1 regular graph. And so also I'd like to prove the conjecture I mentioned about the ferromagnetic easing.
The result also holds the random d-regular graph?
Yeah, so
Which result? If you replace 1 with e to
yeah.
Yes.
And I think that should be d+1 regular. Yeah. But that's, I mean, that you can prove with sort of de Bruijn type conditions. And another sort of question in this general area that I've been thinking about is, does the uniqueness threshold on, or reconstruction thresholds on random graphs can correspond to reconstruction thresholds on trees in some models, and uniqueness thresholds on trees in other models. does it always correspond to one or the other?
So what example do you have where it provably corresponds to a reconstruction on the tree?
So Montanari had a paper recently where he showed that if you have some replica condition, then the reconstruction threshold on the graph corresponds to the reconstruction threshold on the tree. And so, an example of, so they gave a spin glass example for this. I think, I'm not sure if the calculations are done, but an antiferromagnetic easing model would also apply here. I mean, when I say reconstruction threshold on a random graph, it's a finite graph, so sort of it's taking the limits in the right order. Yeah.
But maybe in ferromagnetic systems it should always correspond to the unique.
Yeah.
Maybe the reconstruction should always correspond to.
Yeah.
The reconstruction on the graph correspond to uniqueness on the tree.
Sorry?
Maybe in ferromagnetic models, reconstruction on the graph should always correspond to uniqueness on the tree.
Yeah, that sounds quite plausible. Okay, that's thank you.
So in your work, you have like one, because you prove a quench version, right, of this thing. So do you have like a geometric condition? If a graph has this condition, then if this is called with e to the minus 2, then
Yeah.
that would happen next.
Yeah, so for the easing model, we have that
So is the condition essentially up to half log, and it has to look like a tree?
yeah, more or less. So depends on sort of, yeah, so it depends, so it has to be a tree plus some sort of, the number of edges is sort of at most sort of order log n, and then yeah, that's essentially it. So in terms of the growth of the ball around a point.